So in this module, we are going to have a look at important BJT configuration. So there are three important BJT configurations in which the BJT can be biased. One of them is common emitter mode of the BJT. Another is common base mode of the BJT. And third one is the common collector. When we say a common emitter mode of a BJT, let us have a look at this circuit diagram. Here, the input is applied to the base and emitter is grounded and the output is taken from the collector. So we can say that emitter is common to both input side, which is base, and the output side, which is collector. So the input is applied to the circuit between base and emitter, and the output of this circuit is taken from collector and the emitter. Now, from the collector to the supply voltage V plus, there is a resistor called RC is connected, and accordingly, this circuit will work in a common emitter mode. The DC biasing conditions of to set the operating point of this circuit is not shown yet. Now, from the small signal model not discussed here, we can get the expression for the transconductance of the device, which is indicated by GM. So GM is simply the ratio of current divided by voltage. Now, what current and what voltage? So GM is equal to the output collector current IC divided by the input voltage VBE that we apply across base and emitter. Now, this type of configuration is used so that the BJT can be used as a voltage amplifier. It can also be used as a good current amplifier. Now, the typical current high gain it offers is about 200. It means for a very small signal level of currents, you can have a large level of currents in the output. Similarly, it can also give a small voltage variations that can result into large voltage variations in the output. Now, it offers a medium input resistance. So if you look from the input side of this BJT, you can say that it offers the medium input resistance. And if you look at the output side of this BJT, it offers you a high output resistance. So these are some of the characteristics of the BJT operating in the common emitter mode. The final one is when you apply a sinusoidal voltage at the input, the output will be always 180-degree phase out of phase of the input signal. So there is a phase shift of 180-degree. So to this circuit, there is some drawback. Therefore, we need to look for alternative, improve the circuit and improve its performance. So first, let's have a look at what is that drawback of this circuit and what is called as emitter degeneration and how the circuit can be modified. So for this simple circuit, where we see that there is a resistor RC, input is applied across base and emitter, output is taken across collector and emitter. The gain of this circuit is a strong function of both the temperature and the bias current. So if the temperature fluctuations comes or the bias current differs, the gain, which is the ratio of output by input, will vary. So it is quite unpredictable for this circuit. Second drawback is the stability of this circuit. You need to have an output gain to be stable across all frequencies. But due to any unintentional positive feedback that may be present in the circuit, the stability of the circuit can be affected. Also, there is a third problem with this circuit, such as low input dynamic range. So low input dynamic range is determined by the small signal model of this circuit. So it is imposed by the small signal limit of this circuit. And because of the lower input dynamic range, the circuit output produces high distortion if the low input dynamic range is exceeded. So if you have a large input signal and which goes beyond the small signal model of this circuit, the output will be distorted. So in such case, the transistor ceases to behave like its small signal model. It is not a linear amplifier and it doesn't give you a good output condition. To alleviate these three problems, such as gain, stability, and low input dynamic range, which results in a high distorted output, you can have a small modification of this circuit. What you do is that from emitter to the ground, you place a small value of a resistor called RE. It is called as emitter degeneration circuit. So you modify the circuit from this end to this end. You can see that now the gain of the circuit will be set by purely the ratio of the two resistors, that is RC and the RE. We'll see that in a moment. Now, as we said that to elevate the drawbacks of this circuit, we will use this kind of emitter degeneration circuit where we have placed the value of the resistors. Note that the transconductance of this circuit is simply called as GM, but with this circuit modification, the transconductance gets modified to GM times RE plus 1. And when this value get placed in the voltage gain equation, you will see that the voltage gain is no more dependent on the intrinsic parameters of the transistors. Rather, it is set by the ratio of the resistors. So we see that the addition of the small resistors is called as emitter degeneration. So because of that, because of adding the RE reduces the overall conductance. Therefore, the overall gain will be reduced. So here we see that the voltage gain is given by the expression, which is the ratio of output voltage divided by the input voltage. When you don't have a emitter resistor in the circuit, so for example, when we have a gain of this circuit, it is simply minus GM times RC. That is the gain of this basic circuit. Because you see, when you put RE equal to 0, this expression becomes minus GM times RC. And the gain of this circuit depends on the GM, which can vary due to the temperature and the bias current. However, with the addition of RE, the gain of the circuit is set by this expression, which is minus GM times RC divided by GM times RE plus 1. So this factor comes into denominator and reduces the gain by this factor. So assuming the GM times RE is very, very greater than 1, we can get rid of the GM and the gain is approximately equal to the negative ratio of the two resistor RC over RE. So we can say that the voltage gain for the common emitter degenerated circuit as shown in here is purely set by the ratio of resistors and is independent of the transconductance, unlike this circuit. So therefore, the circuit such as this is preferred for overall improved performance. Finally, the value of RE, we say that AV, that is the voltage gain, is reduced. However, the overall other performance gets improved.